Hello everyone, I am Padma Nilaya from Laser and Plasma Technology Division of Bhabha Atomic Research Center, and I'm going to be with you for next several lectures. You have already learned about the basics of laser, the operation of a laser, the gain medium, the resonator, and also several types of lasers. For example, you have studied atomic gas laser, helium neon laser, the liquid laser, which is a dye laser, the ionic, atomic ionic laser, that is argon ion laser, or solid state laser, which may be an ND YAG laser or an ND glass laser. So today I'm here to tell you about another type of laser, a molecular gas laser, specifically a CO2 laser. Now, you people must have come across CO2 laser somewhere or the other, sometime or the other. That is because of the very versatile applications that a CO2 laser has, whether it is in manufacturing industry, whether it is in medical industry, whether it is in research, spectroscopy, research area, or even environmental monitoring, pollution monitoring, etc. So, what makes this CO2 laser? We are talking about a gas laser, a CO2 laser, so much more different from what you have already studied. Well, the most important difference is that the levels which are participating in the lasing action in a CO2 laser are not the electronic energy levels, but the vibrational levels. They are called rotational vibrational transitions, which happen in a CO2 laser. And we will, at this point, say they are vibrational levels. As we go ahead, you will know that they are low vibrational transitions which are happening here. At this point, let us say they are vibrational. So the transition is between vibrational levels. And what is a molecule? A molecule is a system which consists of more than one or two atoms. So a molecule, apart from having electronic levels, the ground electronic state, excited electronic states, because of the interaction of the atoms with the other atoms that constitute the molecule, it also has vibrational levels, it also has rotational levels, and therefore the spectrum, the spectroscopy of a molecule is much, much more richer than an atomic spectrum. Before we go any further, let us first understand the salient features of a CO2 laser. It was invented in 1963 by an American Indian scientist named C.K. Patel in Bell Laboratories of USA. So it was just 3 years after the invention of the laser. And as we already spoke about, it is a molecular gas laser which operates in the mid-infrared region, that is in the 9 to 11 micron region. Well, where does this mid-infrared region come in the electromagnetic spectrum? So if the electromagnetic spectrum with increasing wavelength in this direction along the positive x-axis, then at the extreme end, that is high energy, is going to be say gamma, followed by X-rays, followed by the UV region, followed by the visible region, followed by the near infrared region, followed by the mid infrared region, followed by the far infrared region, and it will go further to microwaves, etc. So the dye laser that you have studied, or the red helium neon laser, falls into this region of visible spectrum. The solid state laser that you have studied, which is ND YAG laser, operates at 1.06 micron. So it is in the near infrared region. Whereas the CO2 laser that we are thinking at this point of time is operating in the mid infrared region of the electromagnetic spectrum. Now, we have said it operates between 9 to 11 micron region. Normally, a CO2 laser is not continuously tunable in this 9 to 11 micron region, unlike the dye laser that you have seen, which has a continuous tunability over a certain region. This is discretely tunable. What do you mean by discretely tunable? That means it can operate at certain wavelengths in this wavelength region. And why it operates only so discretely, that we will get to know later on. But there are certain CO2 lasers which can be made to be continuously tunable in this laser, in this region. And those are special lasers, and you require some special requirements to be satisfied for it to be operational in a continuous mode in this wavelength region. Now, any laser has to be pumped to get inversion. So the mode of pumping in a CO2 laser is discharge pumping. Like your helium neon laser, where you use an electric discharge, we use discharge here as well to get the inversion in a CO2 laser gas mixture. Although optical pumping, that is using another laser, it is a hydrogen bromide laser, it can also be used for pumping a CO2 molecule. However, this type of pumping, optical pumping, is not very popular because electric discharge pumping is efficient enough and we get a good efficiency, highly efficient operation of CO2 laser. Now, the CO2 laser can be operated in continuous mode, quasi-continuous mode, in pulsed mode, and also over pressures ranging from millibar, millitorr to atmospheric pressure to multi-atmospheric pressure. Because of these wide-ranging operating conditions, the output pulse, that is the temporal pulse duration that you can get from a CO2 laser, can also be widely varying. It can be CW, milliseconds when it is quasi-CW. When operated in pulsed mode at atmospheric pressure, you can get about a microsecond. If it is Q-switched, it can go to even few nanoseconds. The quantum efficiency of CO2 laser is very high of this molecular laser. Generally, molecular lasers will have a very high quantum efficiency. Why it is, we will know later. It has a high quantum efficiency of about 40% and also a quite a high operating efficiency of nearly 15 to 20%. I hope we know what quantum efficiency is. Suppose these are the two the levels between which your transition is taking place, and this is the photon, output photon, because of the lasing action. So IGNOU is the output energy of the photon, whereas the energy required to pump the upper laser level is IGNOU in. It can be photon or it can be some other way. So the ratio of these two energies tells us what the quantum efficiency of a laser is. And quantum efficiency for a CO2 laser, as we have just understood, is almost about 40%. And therefore, CO2 laser is most powerful laser operating in the mid-infrared region that is used, as I said, in manufacturing industry for cutting, drilling, welding, marking, etc. And it is also the first molecular laser that has been used as a photon scalpel, that is light scalpel, to create incision on the skin. That is also, you will probably understand later, that is because mid-infrared region photons have a good absorption in the water molecules that are in our cells, and therefore it can act as a very fine scalpel. Now, let us come to let us revisit what we already know. What is the requirement to get lasing action from any system? Well, the first thing is you need to have an active medium. The active medium is the gain medium, where you have, in this case, molecules in which population inversion is created. So we require to create population inversion. How do you create population inversion? By pumping. So once pumping is done, population inversion is created, then stimulated emission sets in from spontaneous noise. When such an active medium in which population inversion is created, which is where stimulated emission is almost taking place, if you put it in a resonator cavity consisting of highly reflecting mirror M1 and a partially transmitting mirror M2, then photons which are given out axially will undergo to and fro transitions between these two mirrors and will create more photon flux, and you will get a lasing action and an output through this partially transmitting mirror, provided the round trip gain exceeds the loss, that is the threshold condition is met. So this is the resonator. Now a CO2 laser is nothing much different. So we have this resonator cavity and the active medium is the CO2 molecule, we already know. However, it is not just, the lasing gas mixture is not just the CO2 gas, but it actually comprises of a mixture of CO2, helium and nitrogen in the right proportions. And the population inversion is obtained in CO2 by means of electric discharge. The discharge heat, as we all know, because it is not 100% efficient, there is always a lot of heat. So the discharge heat is removed by means of flowing water in the cooling jacket. And in a discharge, they can always be, the gas can get contaminated. CO2 can break into CO and oxygen, and therefore the lasing gas mixture can get contaminated. And therefore, to maintain the efficiency of the system, the gas is generally flowed through the discharge zone and taken out in a rate which maintains the efficiency of the laser. Of course, of late, you also have sealed off systems where some catalyst is made use of to reduce the contamination or to bring back the lasing gas mixture to its normal ratios. So now we've been saying that CO2 is a molecular laser and molecular lasers spectroscopy is different from that of an atomic. The molecule has a different spectroscopy as compared to an atom. Why? Because let us consider a very simple case of a diatomic. So what we have here, we have two atoms, A and B, which are separated of mass Ma and mass Mb, which are separated by the bond length. This bond length will depend on the type of bond that these two atoms share. The chemical bond that happens between these two, which is responsible for the formation of the molecule, that will decide this bond length. And at any given time, this has an average value R. Now, when this molecule is made, suppose we give energy to this, the molecule for certain energies only, and this energy, quantum of this energy will be much, much less than the energy required for the electronic excitation. Even at that energy levels, it is seen that this molecule starts vibrating. Vibrating means the bond length, as you can see here, this is the average bond length. This bond length increases and then it reduces, increases and reduces. So basically what is happening, the molecular vibration is essentially a periodic motion of the constituent atoms about the center of mass. Why we are saying about the center of mass? Because the center of mass does not move in this periodic motion. There is no linear translation of the molecule. The molecule is at the same place, but the constituent atoms are undergoing a back and forth motion as if they're connected by a spring. So basically, what you can show is, you can think of the two atoms as being connected by a spring, and when it is excited and the vibration is going on, the spring stretches and the spring contracts. So the bond length increases, bond length decreases. So this is a kind of simple harmonic motion that is happening between the two atoms. This is a two-body problem, and we can actually translate it into a more easier version of a single body problem, where we think of a single mass of single body of mass mu, which is the reduced mass, that is given by the product of the two masses divided by the sum of the two masses, connected to a rigid wall by a spring with a spring constant K. Now, the moment you look at it, you are reminded of the simple harmonic motion of a mass, and the frequency of oscillation is well known to us, which is given by mu0 is 1 by 2 pi under root K by M. What is this K? K is the spring constant of this spring. and m is nothing but this mu, which is the reduced mass. Okay, so this oscillates at a particular frequency, and therefore associated with this frequency, it also has a vibrational energy. Now, like your electronic energy, the vibrational energy levels are also quantized, and the vibrational energy values are given by EV. We'll know what this V is. EV is V plus half h nu 0, where V is the vibrational quantum number and it takes integer values starting from 0, 1, 2, 3. So what is the minimum energy that this molecule can have? That is V equal to 0. That means E is equal to half h mu 0. So now we are talking about this vibration of atoms of the molecule. So then why do not this vibrational motion be seen in a solid? Well, in case of solid, the rigid framework in which these atoms are fixed, that does not allow this kind of motion. But then when these molecules constitute a gas, then this is a non-rigid system, non-rigid framework, and there this vibrational motion is quite possible. Now, so as the vibrational quantum increases, the amplitude of this vibration too keeps on increasing. So what is the separation between two neighboring vibrational energy levels? So as I have written here, E V plus 1 is the energy of the V plus 1th vibrational level. That means V plus 1 will be given by, we know, V plus 1 plus half h nu, and EV is V plus half h nu. So what is the difference between the two? Separation, that will give us the spacing between two vibrational levels. So that will be VH nu plus 3 by 2 h nu minus VH nu minus half h nu. So this comes to h nu. So that means the vibrational levels are equidistant, and they are separated by h nu. H nu, where nu is the frequency of oscillation. So if we think of a pure simple harmonic rotation, how will the vibrational energy levels be spaced? The first one, when V equal to 0, it is half h nu. The next one, when V equal to 1, is 3 by 2 h nu. The next one is 5 by 2 h nu. And it will go on so on and so forth. And they're all separated by h nu. Isn't it? However, this is in the case of an ideal molecule where it is ideal molecule and the vibrational motion is pure simple harmonic. However, what actually happens is, as the vibrational energy increases, that means as V increases, the vibrational energy increases, and the harmonic oscillator deviates towards anharmonicity. That means the Hooke's law no longer remains valid, and the restoring force, which F is equal to minus kx, it no longer remains linearly proportional. The restoring force is no longer linearly proportional to the displacement, but certain anharmonic terms start getting added. And therefore, the vibrational energy then is harmonic energy minus the anharmonic energy. And therefore, the vibrational energy levels start getting closer and closer as vibrational quantum number increases. As V increases, the spacing reduces. As I have tried to show here, that initially the the levels are equispaced, and as the energy increases, the levels are getting closer and closer and closer. And you can also see this is the vibrational energy as a function of interatomic distance. So as the, yeah, so initially, suppose we see that V equal to 0. So this is one of the atom, and this is the other atom, and this is the mean separation between the two. As the vibrational energy increases, harmonic oscillator tends to become anharmonic. You can see that the symmetry is lost, and the separation between the two atoms starts increasing. And when the vibrational energies becomes further much higher, then you can see that the separation between the two atoms is so large that the atoms actually, the two atoms go separate ways. That means the molecule gets dissociated, and it no longer exists. So when it is in a molecule, when there is a proper bond between the two atoms, then the vibrational energy is negative, and the oscillation is harmonic. And as the energy increases, it tends to be anharmonic, and the molecule eventually dissociates even when it is in the ground electronic state. So we have not given it energy enough to go to the electronic excited state, but even in the ground electronic state, the vibrational energy can become so high that the molecule dissociates and the atoms go their separate path. So what I have shown here is the electronic level of the molecule, the ground electronic level, and the first excited electronic state. And the difference between the atom and the molecule comes here, that the ground electronic state is further populated by vibrational energy levels. And these vibrational energy levels are equispaced as long as the quantum of vibration is low, and then they tend to get closer and closer. And the same thing happens also for the electronically excited state, where there too you will have the vibrational energy levels. The smallness of the vibrational energy as compared to the electronic levels is visible here, right? So these are the vibrational levels. Now, is that all that we have in the spectroscopy of a molecule? No. A molecule, while it vibrates, it can also have a rotational motion. That means the molecule, in addition to vibration, can also go into, okay, I just forgot one thing before. See, energy of a molecule in the ground vibrational level, V, when V equal to 0, is half hν. Okay. This is called 0-point energy. Why does a molecule need to have this 0-point energy? You may be able to explain this from the Heisenberg's uncertainty principle. Maybe you can just think over and probably try to understand why this 0-point energy is very important. Coming to the rotational motion of a molecule. A molecule, in addition to its vibrational motion, can also have rotational motion. Now, let us consider once again a simple diatomic molecule comprising of two atoms, A and B, with masses Ma and Mb. And this is the bond length between the two. Now, the center of mass of this molecule will be closer to Mb, because we have shown Mb to be greater than Ma. At least from the size you can make out that Mb is larger, it is heavier as compared to Ma, and therefore the center of mass is closer to Mb. And so this Ra plus Rb is equal to the bond length, that is R, and we know Ma into Ra is equal to Mb into Rb. Now, when this, suppose our axis of rotation is perpendicular to this board and the atoms are rotating in the plane of the board, then MB subscribes a smaller diameter as compared to MA, which subscribes a larger diameter. So the moment of inertia for this is given by I is equal to MA RA square, MB RB square. From the three equations that we have, that is R is equal to RA plus RB, MA RA is equal to MB RB, you can actually substitute, you can actually get to this equation where moment of inertia I can be given as mu into R square, where mu is equal to MA MB, once again the reduced mass, MA MB upon MA plus MB. This is the reduced mass. So we can also, as we did before, instead of a two-body problem, this can also be brought down into a single body problem where we can think of mass of mu, where mu is the reduced mass. Mu is equal to, as we have seen, MA upon MA plus MB, is going about the center of mass, which is at a distance r, given by RA plus RB. Now, any body which is undergoing a circular motion will have an angular momentum. And this angular momentum L is given by I omega. Maybe here it will be easy for you to understand that what we consider as mass for linear motion is replaced by moment of inertia for circular motion, and linear velocity is analogous to angular velocity for circular motion. And like you have half mv square as the energy, translational energy, you have half I omega square as the rotational energy. So the angular momentum L is given by L is equal to I omega, and the rotational energy Ej is half I omega square, half I omega square. So you substitute omega you can say is L by I. So into L square by I square. So that is 1 by 2 L square by I. So this is your rotational energy, Ej. And just as your vibrational energy, just as your electronic energy, this rotational energy of a molecule is also quantized and is given by Ej is equal to, as you can see here, J into J plus 1 H cross square upon 8 pi square I, where J is the rotational. The molecule can rotate but it can rotate only in certain, it can only rotate in such a way that the rotational energy is quantized and is given by this equation. So before we conclude today's lecture, I would like to say that I have just introduced you to the vibrational, how vibrational levels are formed in an atom, and how rotational levels are formed in an atom. And maybe in the next class, we will start with this rotational motion once again and go further to see how these rotational vibrational levels play a part in the CO2 laser action.